Hi everyone, this is Jacqueline Sarandria, the Conference and Meeting Manager for SMTA. I'd first like to begin by thanking you all for attending this webinar that's hosted by the SMTA Capital Chapter. Before we begin, please consider the following copyright statement. Applicable copyright laws protect all presentation materials. Any unauthorized use, duplication, or distribution is strictly prohibited. As for questions throughout this webinar, please feel free to submit them in the chat box, and Norman is going to address them at the end of the presentation. If you have any questions along the way, please feel free to put it in the chat. And with that, Bert, I'm going to turn it over to you and I will pull up the presentation.
Thank you. Hi, my name is Bert Horner. I'm with the Capital Chapter. I am the president of the chapter. We're excited to have you join us for this meeting. Just a real quick introduction to the chapter, to the attendees on the line. Next slide, please. Our chapter supports actually a lot more industries, and a lot of people think because we're connected to outside of DC, we're strictly DoD, government, mil-aero. We have medical research, industrial controllers, telecom, automotive electronics around our area. We have a nice mix of OEMs and contract manufacturers in this area. Next slide, please. Our chapter, who we support, we're basically supporting the Mid-Atlantic area around Baltimore, DC. We get into Virginia, Delaware, Maryland, South Central Pennsylvania, and Eastern West Virginia is our region that we try to support. Next slide, please. We have a great group of officers. Like I said, I'm blessed to have Katie, Karen, Jessica, Brian, Fernando, Robert, and Banu. It's a nice mix of people that have a ton of experience. Like I said, I'm really a lucky officer to have 3 past presidents on our staff, a nice mix of suppliers and end users, and professionals that really know the industry and can get a decent speaker. So I am really blessed with that. We have a great sense of pride in the industry, and industry insight, and all the officers have a good sense of humor. Next slide, please. Before I forget, 2 upcoming events for the SMTA. We have an upcoming webinar in September. I think it's the 16th. We'll send an announcement on Sonic's detection and advanced wafer and packaging level devices using scanning acoustic microscope. And then we also have the very big and the SMTA. We went virtual this year, but it's still going to be a great show coming up, and that's going to be the end of September, going into October. There'll be some rebroadcast, and if you need to get some information on that. That being said, next slide, please. Today's talk, we have Norman Amadeus, PhD. He's going to present design for rinsability, effect of SMT component packaging design on cleaning effectiveness. Next slide. A little bit about Norm. Norman Amadeus he's an engineering fellow at Raytheon, responsible for material engineering, design, material analysis, process equipment development, microanalytic methodology development, product support, technology roadmaps associated with manufacturing of circuit card assemblies used in missile and smart munitions, ground-based radars, and mobile sensors across the U.S. and international sites. Norm has 25 years of industrial experience, has worked for LTV, Lockheed, NASA, Motorola, Intel, Texas Instruments, and American University. Norm holds a interdisciplinary PhD in chemical engineering from New Mexico State University, holds a MS in material sciences engineering from University of Illinois, and Bachelor's of Science in Metallurgical Engineering from Colorado State University. He also has 9 U.S. patents and has 29 peer-reviewed publications. So this man really knows his stuff. We're really lucky to have him. You're not here to listen to me talk, so I'm going to hand over the baton to Norm. Please take it away, sir.
Okay. Well, thank you, Bert, for that introduction. Just a quick update for those who may not know. Raytheon merged with United Technologies, so now we're called Raytheon Technologies. And we've also done a number of consolidations internally, and I'm now with the Raytheon Missiles and Defense Group. So same job, different name, and just different managers. Okay, so this particular presentation, this work was done about 3 years ago, and I presented it at SMTA International. But at that time, we only took it up to the process study. But since then, what's new here is that we've added reliability and thermal cyclic testing. So you can benefit from that if you've already seen this. So let me go ahead and go to screen mode. All right, so Bert, do you see everything here? Am I broadcasting correctly?
Yes, sir.
Okay. All right, so circuit card assemblies, we call them CCAs. These are printed circuit boards with components. And since we're a military aerospace firm, our customers are primarily military and aero. They need to be class 3. So they need to function in a very extreme environment, and often they have to last, 30 years or what have you. And they need to operate like in the Arabian or Persian Gulf all the way up to, Arctic environments. And so one of the things that this product requires, or at least the military requires, is conformal coating. So before we put the conformal coating in the surface of the board or the CCAs, semi-aqueously chemically clean. We remove the fluxes or what have you, so we can then coat, right, run a paint over a clean surface. But if these cleaning solutions get entrained, the soap gets trapped inside there, tight gaps, then we've observed that you may cause materials to degrade, which limit the performance and of the materials, and therefore the electrical performance and the lifetime. So we were very concerned about that. And certain electronic components, recent builds were detected, came out of the field almost. They were already in the final assemblies and already cut into the chase there, and we'll focus on the component housing design, where we felt that was a major factor in trapping these things. So that was kind of a hypothesis, and so we wanted to do an investigation, do some experiments to determine, first of all, this is clean, and if there's certain susceptibility of certain components, and then, as I mentioned, we have talked the efficiency of the over here. And the effect of the cleaning residue on reliability. All right, so that's kind of where we started. So what am I talking about? So here's a component, scales about you know, 5 by 5 centimeters, and or about 2 to 2 on this one, 2 to 4 centimeters. So these is little components. And if you look on the top, here's a hole on the lower left. You see all this gook out there, right? What the heck is that? Just so happens this is pin 1 and it sits over a little hole, which typically is sometimes used so they can cure the epoxy inside and it has a place to escape. So we looked at that, then when you opened it up, all right, when you open it up, you can see that hole there. And we just saw all this green goo, slime inside there. And those little boxes kind of show you that also the ends were the entry were also coming in between the gaps here. Okay, took a look at that, so that'll look good. And then we did some cross sections here, so you can see the one on the top. I don't know how soon you guys see the presentation, but on the top, it's the as received. They didn't do anything. It's a brand new part. This happens to be a little diode with some wire inside of it, wrapping around. And when you cross section those wires, you see that they're pretty well covered. But the one that after assembly here, or after contamination, it's contaminated, you can see it looks really cruddy. And the wires themselves have basically lost their coating, their plastic urethane coating, polyurethane coating. And yet the device still works, but you could tell that these were low voltage, low current. But it didn't look that great when you do the cross section because you start seeing some of the copper itself being degraded. Now, the polyurethane in between is still stuck in there, so it still provides some amount of insulation, but you can see that this is on its way to failure. Okay. So sometimes you see these things and they're working fine because they're passing an electrical test, but that's why you got to kind of catch these ahead of time. All right, here's another one. I had to block out the device part numbers here, but you can see on the top, this is a component cover that's on top of a little board. A little board sits on a printed circuit board. And when we open it up, you are looking here really close at the wires, and there's like gunk and goo in there, in between there. And I'll show you later that this has actually been discolored. And then on the metallic contacts, we saw this kind of corrosion. These are things that are soldered down. And you can see there's copper oxides with chlorine detected. So, and the other part that we found is that we actually found cleaning solution markers in here. Okay, still the cleaning solution was, so we have PIR that can detect the presence of cleaning solution. Solution A. All right, so we had to form a Tiger team, and there was a lot of components. We had like 500 or 600 on our component list, and that would have really caused us a lot of problems if we had to go look at each and every one. So we had to quarantine some of these parts, so that took us a little while. While we're trying to capture these, you have to do some studies. So we look at the most suspected ones and the ones that were failing and say, okay, what this family of part has something funny about it. We'll need to let's check these out to see if they're okay. And if anything were suspected contamination, then we submitted for further study. And we also looked at other databases, right, in the products to see if there is in the field a higher risk. So a lot of things going on at the same time. So this was kind of our first cut where we were looking at the contamination rate versus the component type. So when we opened some of these suspect devices that were coming around here, suspect meaning, okay, these are the ones that were being returned, as well as products, actually suspected products. And we saw there's a whole bunch of them that were contaminated, and there was a whole bunch that were not contaminated, right, all on the right side. So the hypothesis was like, man, is there something about the ones on the right that are easier to clean? So I'm already getting the cat out of the bag. The ones to the right with the green says, started thinking, hey, are those more rinsable? Easier to clean, maybe? And why is that? So we have to start formulate some kind of idea. Okay, so what makes them so unique? Why are these not showing any contamination? All right, so when we started looking at these certain ones that had high rates, we started observing that these component covers, we put them on top, square top, so we can label them on top, and then the automatic inspection equipment can see it, right? You want a flat little top so you can pick it up and image it, make sure the orientation is correct, so it serves that, be able to pick it up, place it. But it also serves to protect the components inside from being hit or damaged physically. And they're usually attached with this epoxy little glue around the side to cure it, put the cover on. But it's not a hermetic seal, far from it. And so there's seams on the opposite sides on this one. They don't put epoxy all around on some of these. Even if you do, that has its problems, so I'll explain that. But here's one that has epoxy on two sides, and we open it up, and where the seam is, we start seeing trails of this signatures of contaminants coming in through the seam. All right, and then we looked a little bit closer, and you can see that, oh, gee, the metallic contacts look like they're getting corroded. All right, so this is the mechanism. So rather than go into reading this, you can read it later. Let me just show you some animation. Okay, there's really two extreme conditions of a component. It could be hermetically sealed with lead glass, what have you. In other words, there's no water or any air that can go in there. Very tight seal. We have components like that that are very sealed. They cost you a lot of money. And the opposite side, I have components that are pretty much open, big windows, if you will, or big doors, and they're very vented. So those are kind of the extremes. So when we clean something, we wash it, and we wash it with the cleaning, and then we rinse it, right? So here, not bad. I clean the component with the wash, I get rid of the fluxes, and I rinse it, take away the dirt, right? Same thing with the vented open one. I wash inside and out, and then I can also rinse, right? Okay, so those are two extreme conditions. But if I have something that has very tight vent holes, those little holes, gaps, seams, then what comes into play is capillary forces. So now I'm going to clean this. I'm in a bathtub, if you will, that has, I have bath water, and I have clean agents and ionics, right? Salts and all that I've taken out. I got the soap and the ionics, the dirt, if you will. And it's inline cleaner. So when I'm washing, the stuff goes in, and then when I rinse, remember, I don't have a very, the wash can go in because it's low permeability, it's low surface tension, so it gets entrained. But then the water has its surface tension, as is DI water, and it doesn't penetrate, doesn't entrain, and all it does is just hit the outside. It doesn't go inside. So what we found is that there's different component housings with different sizes and vents and so forth. And we surmise that a minimum size is required for the part to be effectively washed and cleaned, washed and rinsed. So that's why this is titled Designed for Rinsability, not designed for cleanability. Right? It doesn't do with cleaning. It has everything to do with rinsing. All right, I want to be able to wash and rinse. Okay. All right, so what we observed was two things, two chemical material reactions. One was the cleaning agent was primarily degrading the polymers, the wire insulation. Okay, so you can see below there, the picture on the left shows the as received wire, pristine. We haven't done anything with it. It's very green. But then when we expose it with entrained cleaning solutions, right, and sit inside, it's discoloring, right? It's just the first sign of degradation, right? If its color is changing and the properties are changing. And so when you touch it with a knife and so forth, it's really gummy. And it would basically, it was real easy to remove. Okay, so that was one observation. The second one was that, remember, the bath water also has halides, chlorines, all the salts that come off the fluxes and so forth. And the chlorine is acting like an oxidant, as a catalyst. Right? That's why you always be careful with chlorine. It's insidious. And so here on the left, you can see an as received contact, the wires attached on the base. But on the right, yellow boxes, it started discoloring. Okay. Now, again, these are low voltage devices, so they'll probably work to a certain degree, but eventually you're going to see a failure over time, long time, latent failures. If these are high current, even worse, right? These so happen to be low current. Okay, so there's all kinds of materials out there, right, that we use. These are kind of representative of what is in our SMT devices. A lot of plastics, polyurethanes, fluoride, elastomers, polycarbonates, everything, and metals as well. And there's really three chemistries that we use. We were using chemistry A, and anything that's marked with an X there tells us it's not compatible. This is from our vendors. Our vendors tell us, hey, you got to test this stuff. And for the most part, okay, you can say, hey, as long as I clean it, I should be okay right away. I use it really quick, right? I get into the shower, soap up real quick, and then I rinse it off, I'll be okay, right? But if I take a shower and I leave that soap on me a long time all day, I'm probably gonna start itching, being very itchy that day. So how much time you expose yourself to, for the most part, it's okay if you're in and out real quick. But if it gets entrained and stuck for a while, that's when you risk contamination or degradation. Okay. So the materials on the right tell me that A chemistry is not good for a lot of those, and there's a new chemistry which is much more compatible with more materials. And then C is another one that's used for vapor degreasing, so it also has less risk. You can cover more materials. All right, so you got to be careful what cleaning chemistry you're employing. The graph below it just tells me what is my bath water made out of in terms of anions and cations. So we follow this. This was a study that shows we follow the chlorines, sulfates, bromides, phosphates, and cations. And so the chlorines are the ones we got to watch out. The ions, the anions, are the ones that react with metals. The chlorine is very dangerous. Okay, so how do we go about this? Now that we understand the problem is, okay, how do we go about this, proving this? So what we did, a couple of interns with good eyes, and I had them measure 28 different component housing designs from 2 vendors. And they used a microscope, right, that had area measurements. And then we performed an experiment. We built on a board these same 28 components and ran them through the planing machines. Looked at them and see if they had any residue entrapped. So a lot of roll up your sleeve type of work here. So for example, we measured the vent area measurements. The vent areas were measured on the side, the little vents. Back one, this one had a lot of space underneath. It just totaled up. I have total up what's the area that's open. Okay, for each component type. All right, so that's how we have these vent area measurements, if you will, housing vent area measurements. Okay. So there's the 28 components. All right, I numbered them in the order of increasing vent area. So they went from 0, looked like there was not, like they were well sealed, all the way up to 25 millimeters squared, and it was pretty much open all the way. And I just have an SV ratio here to normalize it, but it tended to track. We'll look at the purple one. So component 1 was pretty sealed from what we could tell, 1 through 4, and number 27, 28, they pretty open. Okay, so we got that characterized. And then we put those 28 components, all right, on the board, randomly. These are just test boards. Okay. And we kept one as a control, one, and then we processed it. We ran it once, one of them we ran once, 2 we ran twice, and 2 we ran 3 times. Okay. And then we baked them afterwards. And after they were baked, we opened them up and inspected all of these and ranked them to a qualitative criteria of contamination. Let's see how dirty they were. Okay, so again, this we start down here. This is the one that's kind of a control. We didn't wash it. We went 1 cycle, we washed and rinsed it. 2, we washed and rinsed it twice. And 3, we washed and rinsed it 3 times. Okay. So that's kind of the basic experiment. And then we baked it afterwards. Okay, so this chart here kind of ranks them again, but in this case, as I said, I ranked the components in terms of the vent area. Okay, for component 1, 2, 3, all these down here, they seemed like they were very sealed. And as you all the way down to 28 or 27, that had a lot of vent area. Okay, so that's along the bottom. And then along the top is just a number of wash and rinse cycles. So if you look back at this, the brown one, it's 1 means there was no wash. So you can almost tell if the more and more I wash, go through the cycles, it seems to clean up, like going from left to right. But again, operations, throw me out of there saying, no, I can't be cleaning these things three times or 4 times. I got other stuff to do. You need to clean these once and be done with it. So, okay. So, but that told us that, hey, you're getting stuff entrained and probably the rinsing is not as effective, and it's probably also getting a little more permeable into the device. And again, versus the red means it's very contaminated, by the way. Green means it's not very contaminated. This chart, I told you. Okay. And started seeing this pattern, saying, okay, seems like the ones that are really open are pretty green. All right. So this is where we first started this graph. And the purple line, as I mentioned before, was the vent area. Right? So going from left to right, the vent area increases. Those orange dots is the contamination. Okay, so that's where we observe contamination. Okay. So you can see on the left, I had a lot of contamination when this vent area was really low. Right here, 1, 2, 3, 4, 5. What the heck? How come with these, they're supposed to be so well sealed, they don't have vent area, are giving me a higher contamination? Okay. So then we had to map this overlay and say, okay, what is it that we're looking at? Okay, so over here on the right, we have to go right. In this category C, which is green, you can see that component there has some big garage door openings there. So it's low risk for entrainment. Okay, so that makes sense. It's way down here and a lot of zeros. And then this one here that had seams, okay, about 1 to 3 millimeter, it also had some contamination, a lot of contamination. And then when you come over here to section A, this is one that's sealed all the way. It's ultrasonically sealed. Right? You would think it'd be a good seal, but if you compromise that seal, it would fail with high contamination. So this is what's going on with this one. This is an explanation for it. So what we observed, now this was an ultrasonic seal welded, started seeing this ooze coming out. And that ooze was the chemistry A based on FTIR. The part was showing the signature, and it matches what our library of that cleaning solution is. Okay, so we know this stuff is coming out. It's going in and it's coming out. Okay, so this is what the mechanism is there. So we start with this one component that we think is so well sealed, ultrasonic welded. But what happens is when we go through a cleaning bath of 150 degrees C and we do other subsequent thermal exposures, then that seal is going to get compromised, right? It's going to open up just enough that the cleaning solutions gets entrapped, and then we do other things. We dry, wet, rework. You've already compromised that seal, and if you keep doing it over and over, clean it again, you're going to make things worse. So basically what happens is that you end up with cleaning residue and ionics remaining. Okay? So that explains why these components that are ultrasonically sealed, don't be fooled. All right, so this next chart is going to get a little busy. Now, let me map it out for you. On the x-axis, okay, is the component cover design or vent area, increasing vent area. And I'm going to show you the component design. So you go from left to right, is the component cover design, increasing vent area. On the y-axis, I plotted rinsability, okay, kind of a qualitative. The higher it is up here on this graph, the low risk for residue contamination, right? The more rinsable it is. Okay. The lower rinsability means high risk for contamination. Okay, on the top, I'm just going to show you the two conditions that we had before, right? Ideal, right? It's hermetic, it's a seal, it's a glass. Okay. And the other one, ideal, is no cover, right? I can clean and rinse, no problem. This just happens to be a device that didn't need a cover because it's flat on top and we can identify it. Okay, very rare, but you can tell, hey, I can wash and rinse that guy, he has no cover on. It's in the middle, which you got to be careful with. Okay? When you have a certain seal of like 1 to 4 mils or openings and very, you know, like if you open a can of whatever water you want to empty up a can, you have to put 2 holes in it, right, to relieve the pressure. Well, here we only got 1 hole, so it'll come in with the heat and capillary, and that is where the capillary forces dominate, and you entrain the cleaning solution, and you don't allow water can't get in to rinse. Okay. So as I increase that vent area, here are different configurations, and I was just showing you the ones, there's pictures in there, these components. So as I increase that vent area, you end up being aqueous washable, right? The vendor will tell you, you know what, you can wash this one. And here's one that's open on the bottom, and of course you see the one on the top that doesn't have no cover. So the increasing vent area, the rinsability goes up, right? You're going up on the y-axis. Now that one that I was showing you that said, man, that should be a good one, ultrasonic well, I should be able to wash and rinse this guy and not worry about it. The problem is thermal processing, as I discussed, right? You heat that up, it'll fracture, and it ends up behaving exactly like one that has a seam. And that's why we saw these components entrained combination to a high degree. All right, so basically, we now have our little Nike swoosh here that tells you rinsability, that vent area. If you keep it above 5 millimeters squared, you should be safe. And you can bring your risk down here at the bottom, right? If you're in the capillary, you're really risky it. So you're better off being over here than over here on the left side. Okay. So on lifetime reliability testing, we're doing on time here. So what we did here is take a board, and we intentionally injected different amounts of cleaning solution. So we took one board, one size control, I took two components and put 40 microliters of cleaning solution, 1 and 3 in another, and I went through this testing, humidity testing, increasing amounts, 89 hours, 107 hours a day. And then we finished with thermal cycling for 50 or 100 or 50 or 200 cycles, just to see what would happen if we had components that had the solution in it. We looked at insertion loss, input loss, all these different electrical variable plots, like I tortured you there. We just focus on insertion loss, which is an important one for this device. Okay, so here's the control part. The spec was 1.5, and 1.3, 1.28. As we went through every time there's just a leg, we tested it to see if it would degrade. And then one with the 40 micron liter, microliters of solution, it dipped below slightly. And 20 microliter also dipped below a little bit. Yeah. On average, it's still in spec, but this one was saying minus 1.47. They were just under spec of 1.5. We're pushing it. So essentially what we saw here is just a summary that based on this, we saw about a 12 to 13% degradation. Still within spec. So you can grade these. Again, this is kind of a worst case, so you got to be careful. So in summary, the component housing construction was the major factor. We saw a definite relationship between the vent area and the train contaminant. Now, for those that were very well bonded, their thermal processing effects, they can compromise the body interface seals. So don't be fooled. Putting more epoxy around there doesn't need the more the better there. The humidity testing and thermal cycle testing showed that, you can get discoloration, degradation about 10 to 15%. But again, ended it within specification, at least this time. So basically, certain components have more rinsability than others. right? So we've already implemented that, some guidelines here. So this is kind of the recommendations. So you gotta identify the materials used in there, make sure your cleaning chemistries are understood, right? You may want to go to a less aggressive cleaning solution, what we did, and better target what we want to clean. And again, evaluate the instructions for rinsability and the covers. And basically follow those 4 things down there. Make sure your vent area is a little bit bigger than 5 millimeters square. Make sure you avoid the gap. You don't have any gaps or seams. Make sure that it's bigger than 4 mils. Have at least 2 vents, 1 inlet, 1 outlet, a front door and a back door, and locate them accordingly, right? And this was the team. Thank you. And that's all I have. Any questions?
Thanks, Norm. That presentation was really great and provided us with a ton of good information. For those of you that are listening in right now, if you have any questions for Norm, please submit your questions now. And it does look like we have 1 question so far. The question is, are these vented components considered washable by the supplier?
Well, that's a good question. That's the first thing you look for on their site. And most often, the ones that are washable, they'll say aqueous washable. On others, they'll say silent. They won't come in and declare whether they're washable or not. So you gotta kind of look at the design and make a call.
Okay, the next question is, can you provide a bit more information about the I'm going to mispronounce this, I apologize, semi-aqueous and solvent cleaners without becoming commercial?
Upcoming commercial. Well, when we talk about semi-aqueous, it means that we're having a soapy solution that has various surfactants, and they're kind of targeting. In our case, we're cleaning no flux cleaning solutions, right? So it's kind of an oxymoron. You know, we're using no clean paste, but we still clean them to, as I mentioned before, we still clean off those flux because we need to conformal coat them afterwards. So there are different chemistries. There's also other kinds of fluxes that are more acidic, right, where they can be more aggressive. But there's a number of vendors out there that go to their sites and they'll tell you which semi-aqueous clean chemistry works with your application.
Hey Norm, just a quick thing. It sounds like there's a bit of background noise coming from wherever your microphone is, so I'm not sure exactly what that is, but just so you're aware.
Let's see if I can move. Sure. Okay, how about now?
Yeah, that sounds good. Thanks. The next question is, would you agree that having vents near the bottom of the components is better than at the top?
Yes. I went back on the presentations, so the vent locations opposite of each other and on bottom. So use gravity to help you out. If you put the vents on the bottom, most of the electronics are in there, right? They're not really up high, so yeah, you want to put them on the bottom. So you're more close to the printed circuit board side.
Okay, the next question is, would a relay with damaged lead seal behave similar to component with vent hole during wash?
Effectively, yes, right? Let me go back here. Oh, so you can see the one up on the top, that lead seal there. And these are nitrogen. Sometimes you'll see them as nitrogen-filled components, right? But they have a glass seal. It's hermetic, meaning gas. Now the hydrogen molecules cannot penetrate. So those behave identical, at least in terms of rinsing, compared to the one all the way to the right, which says there is no cover. So you can see the purple rinsability is very, very high and low risk for contamination. But if you're a designer and you're making parts and so forth, these are expensive here. These ideal ones in the upper left, right, cost you a lot of money. The military does have some applications where they want to have a hermetic seal. But if you can get away with a cover that has a lot of venting and so forth, that's really where you want to be. Okay, you want to be over here. You got more latitude. Here, if you start playing with ultrasonic welds and more glue and all that, you're risking delaminations and compromised seals. And you'll end up like these guys down here, these pink ones here. You know, these seals that aren't quite sealed. Right? And that's what we found is these guys were the ones we had to quarantine, get them out, and we worked with vendors to see if we can replace these and or give us better openings or plug these holes, you know, things like that. I don't know if I answered the question.
Well, we can wait to see if they send in a follow-up question, but are you all right with if I move on to the next question?
Absolutely, go ahead.
Okay. We are starting to observe convergence of advanced packaging and SMT technology, especially with case of 2.5D and 3D packages. For example, Altera type packages. What would your recommendation of these packages, well, I'm sorry, it's just typing a little over. What would your recommendation of these packages are being used, and what would you recommend to redesign the lids or possibly have a no clean process?
Yeah, if you have a no clean process, again, for military applications, it's not going to be viable, right? Because you have to conform with code afterwards. So if you're in a commercial space, you know, say like an Intel or a TI, your boards are no clean, right? But they only last, you know, 3, 4, 5 years. And so the risks are pretty low. But for military applications, unless you can change the military mindset, no clean process. So you're not cleaning, it's not acceptable. Now going forward, what we tell our design engineers here and so forth, we have a library of parts and so forth that they can reference, but it just has to go to fundamentals. You look at your package and you look for there's any possibility, any seals or gaps, anything like that you want to look for, and understand could these open into where electronic circuitry is, they're tight, and you want to look at that. If you suspect, hey, this has a lot of gaps in it or seals, what we do is we'll do a quick evaluation. We'll dip it in a cleaning solution at that temperature and for 8 hours or what have you in the lab, and then the lab will take it out, rinse it in alcohol, and see if any chemistry comes out. And that'll tell you, you know what, this part is absorbing this cleaning solution. High risk. And we've done that on some of these parts. If they're not an obvious one, they'll say, gee, let's go try it. We'll run it in the lab, right? We'll soak it in 15% solution or what have you, heat it up, and then again put it in an alcohol bath and draw off the chemistry and perform IC, right? Perform FTIR, right? Basically come back here and perform this kind of test. Okay, so that's kind of what the rules are. Is to there's guidelines, but you need to kind of base yourself on fundamentals and say what what do I look for? Try to get back to, you want to make sure you look at your components. You want to make sure you got a clean solution. It's not, it's designed for your process, not clean, whatever. And then evaluate the component constructions. Tell your engineers, your designers, and it takes a while, right? And then but on our designs and so forth, that's a question that's asked. Is your component aqueous washable? And then they ask the vendor. Sometimes the vendor says yes. Sometimes the vendor says silent. We don't know. And that's when you have to, right? How do I assess this before I build it?
All right, the next question is, for a given vent area, how important is the aspect ratio of the opening?
It didn't seem to matter. You want to make sure that the height wasn't more than 1 or 2 mils. But if you had so here you see the gap of 1 to 4 mils. If it was very long and you had a very long aspect ratio, it would still entrain it. Okay? Because the capillary forces don't really look at that area. But what we tried to do, because we didn't think about that, is try to plot the vent area to the surface area. In other words, I had a real big component, a big house, and in other words, I have a big wall on the outside, and is there a relationship? We didn't really see it. It seemed to be the same, but again, most of these components are in the 1 to 2 centimeter X by Y, or half a centimeter up to 1 millimeter. So I think the main thing that we saw was, what was the openings? You can come down here and figure out, get yourself into a rat hole trying to figure out aspect ratio and all that. But I think if you look at the designs past 5 millimeter squares, that's what you need to focus on. If you have big openings that can be easily rinsed, that the water can get in there, then you'll be safe. You want to play with aspect ratios down here, you're probably risking it.
Okay, the next question is, have you performed the same type of analysis on vented BGAs? Any recommendations on washing assemblies with vented BGAs?
Well, many of these had started before we got this particular product. And I don't know if the packages are BGAs, but there's some components out there. I think the one I customized, Xilinx makes them. And we had worked with them. They had a vent hole on their, we'll call it a BGA. So BGAs themselves, I don't think I think you still have a higher standoff with BGAs. So I don't see that, but the Xilinx had some holes in there, and they have since changed their design. That's the only BGA I know of. But if this is a BGA, you may have underfill, and if your underfill is performed, I don't think we've ever seen any contamination heated in there. And remember, a BGA kind of sits kind of high. And I think you got more space in between BGAs than you would between the seams and so forth. I'm not sure there's capillary forces under BGA. No, we didn't really do it on there because we never got any reports of disbonding or residue trapped under ETAs.
Well, it looks like that was the last question from today. So Norman, thank you very much for sharing your knowledge with us today and taking the time to present on behalf of SMTA and the SMTA Capital Chapter. We really appreciate it.
Oh, that was great. Really good questions. Good questions.
Well, to all of you that are attending today, we welcome any further comments, suggestions, or input that you have. So a short survey will be delivered to your inbox once the webinar concludes, and we kindly ask that you take a few minutes to complete it, as it's helpful to Norman, the Capital Chapter, and SMTA headquarters. With that, Bert, did you have any final words for the day?
Just thank you for attending. Thank you, Norman, for a great presentation. I think we found it very insightful, and we value your time. Thank you so much.
All right, thank you to all of you, and enjoy the rest of your day, and hope to see you at the next SMTA event. Thanks, guys. Have a good day.
Okay, thank you.
Thank you.
Bye-bye.